particularly comes up a lot in, I think, applications in Africa is spatial data analysis. John, who's been at Makerere University for a number of years, still a visiting professor there. Also now visiting, what are you visiting? You're visiting at Sheffield, University of Sheffield. You're visiting at University of Edinburgh. John's just visiting everywhere, but his main association is Pulse Lab Kampala. And of course, John has really been the heart of driving forward the use of data, this vision that he's had for a number of years of driving forward applications in the developing world with the most advanced technology. So, which is something that's really, really inspired me, and I know a lot of other people. So we're really lucky to have John. Well, it's kind of odd because we wouldn't really be here without John in many senses. So we're not really lucky. It's just a natural consequence of events. But he's going to tell us about spatial data analysis.
Oh goodness! Thanks, Neil, for those kind words. Yes, I'm a professional visitor, basically. If anyone wants to be visited, just let me know. Delight to be here as usual. I mean, it's just amazing what's happening each year. It gets bigger and better, and the level gets higher, and what people are doing is always moving forward. And it's just really exciting to think what's going to be happening, and what you guys are going to be doing in a few years' time. So when you reach the corridors of power, don't forget about us. Okay, so spatial data analysis. This, as Neil said, this came up a few times when we were planning the program. There were some requests. Can we look at this? Dina was saying a few people here in TZ were interested especially, so we thought we'd introduce this. And this is really kind of bread and butter stuff, particularly in the Pulse Lab Kampala, where the goal of the type of analysis we do there is to have insights at this kind of national or population-wide scale, and then really you need to put stuff on maps, make different types of inferences, and display them in the appropriate way. Happy to kind of go through some of the things we've done. How I'd like to structure this next hour, I'll be talking, hopefully with a bunch of questions and interaction, and then for those who are interested, we'll have a practical later on at 11. And what I'm going to do is start by showing some examples of things we've done in Uganda, because a particular focus of these sessions is to try and show data science and machine learning in the context of things that can be done here. And then we'll go through some of the techniques and a bit of a kind of example analysis here, which will lead us into the practical later. Okay, so example one. This is something which pertains to some interesting comments Neil made in his intro in the first session, that in kind of classical data analysis or lots of traditional stats, you get to design the data that you want. You design your survey instrument, your questionnaire, or your sensor measurements or something, and then you make them be what you want them to be to feed into your analysis, and then analyze that. And there's this whole new world of data which is produced as the byproduct of something else, and it's up to our kind of ingenuity and imagination to think what can be done with it. So what we see here is a map of travel times within Uganda. Kampala is at the epicenter, and these contours show the time in hours to reach different places. So 2 is like where you can reach within 2 hours, 3 hours, 4 hours, and so on. And this was calculated with telecoms data. This is from a mobile phone company, and it's people making and receiving phone calls. So anyone who made or received a phone call this morning from a cell tower in Arusha, and then now they're here in Nelson Mandela, and they maybe have more activity on their phone. That's kind of one record in the billing database of your telecom provider. That person, or at least that SIM card, has moved from there to here. So now imagine doing this on a population-wide scale. You have many tens of millions of call events per day. And the nice thing about that is you can work this out day by day, hour by hour. So let's kind of roll the clock here, and we'll see like a 4-week progression. And so these travel times change according to weather, time of day, time of week, accidents, that kind of stuff. So, you know, how far you can get in like X number of hours journey varies quite widely. And, you know, you can sort of see the further away you get to Kampala, the longer the journey, the more stuff that can go wrong, as the people who traveled by bus from Kampala are painfully aware. So this is an example of data which you know, isn't exactly sort of a spatial data set as it began life. It's something that the mobile phone company uses to keep track of like how much you owe them. But it can be converted into spatial data sets with some stuff that we will talk about. Another kind of interesting like movement data set. Yeah, okay. So these are boda bodas in Kampala, little motorbike taxis buzzing around, and the data source from this is GPS anti-theft trackers. So we had an agreement with the company which makes these to do some data analysis, and so for each of these little kind of particles here, that's one motorbike, and we're seeing a trail of its last kind of 30 seconds, where it's been. It's color-coded by velocity, and this kind of stuff. So again, it's like repurposing of data, which can be used for all sorts of useful stuff, you know, public, you know, urban planning, or looking at connectivity, or traffic patterns, that kind of stuff. Another example, very important spatial data example, and a big data example that we need our techniques for, is remote sensing and satellite data. So this is vegetation strength. This is normalized difference vegetation index, so basically how green is stuff, something like that. And we can see the kind of seasons here, you know, which places are getting dry and where is the vegetation flourishing. Useful for all sorts of things. You know, even in itself, imagine you were to predict, you know, to take a particular area and predict like what's the vegetation going to be like next month. That kind of seems like it should be something not too difficult to do, but it turns out, as we've been discussing, this is actually very difficult and really at the forefront of the research into what our processing methods can do. You know, you have lots and lots of pixels here, trying to work out the relationship with one pixel in future with everything you've seen in the past is actually pretty tough, but also quite interesting. So big data sets, you know, when you start, you know, if you download a year's worth of data, it's easily, you know, in the hundreds of gigabytes. And so, you know, even reading it in or producing summary statistics is already kind of difficult. And so, thinking about how to extract the information you want, you know, you need to use some tools. Another one here is this is some work we did in 2015. There was a typhoid outbreak in Uganda, and the PulseLab Kampala was part of the National Task Force on Typhoid. And we were in the meetings in Ministry of Health where people were trying to work out where the problem was and what the trajectory of infection was and what to do about it. And we produced from the data there a few different ways of kind of visualizing and trying to understand how the situation was unfolding. What we see is infection rates of typhoid. That's the choropleth, so these kind of colored polygons, which are sub-counties. Darker red, the more typhoid cases. And these sort of ripples, these movements coming out of places are this same data of movement from telecoms from the places which were infected above some certain threshold. And so this is the kind of stuff that can feed into analysis of, like this kind of what's going to happen next question. So there's this panel here on the left, which is kind of from Mbale, this place in the southeast. And we can kind of see, like, there's this place where it's quite infected near the border, and then there's movement from an infected place to an uninfected place, and so that signals that there may be a risk of infections cropping up in that new place. And so where there are scarce resources which have to be allocated, particularly prevention resources, you know, sanitation measures and visiting health centres to make sure they're not stocked out of sanitary supplies, that kind of thing, then, you know, that could be used to target those. So one last example of analysis we've done is to do with biodiversity, and we did some work for UNDP in Zimbabwe, and what we were doing was taking many different existing data resources and just kind of putting them on top of each other and calculating some simple statistics to be able to kind of put things in context. You know, so we have here, like, where are the protected areas within Zimbabwe? We may also want to see, you know, what's the human footprint? This is something NASA calculates from satellite data. You know, where has deforestation occurred? You know, that's another data set available somewhere else. All of these data sets were freely available online, and we just kind of put them in together. So there's a whole load of different layers and sort of things we can extract when you have these things together. One thing which is, you know, really pulls this out for me is, like, where are the protected natural areas and where are the areas of mineral deposits, coal or gold, or there's this great dike which has many gemstones in Zimbabwe. And so you kind of know that, like, wherever these places intersect, that's going to be a problem, right, at some point in the future. So whereas these data sets exist separately, you know, just by bringing them together and doing some very simple stuff, that's pretty useful. So those are the examples I'm going to show of work we've already done. Does anyone have any questions about any of that before we move into kind of tools and techniques? Yeah. Okay, so the question was of the vegetation example. What was the input data? So this is something you can actually download this vegetation data directly, but it comes from so one way to think of a satellite is it's kind of a sensor which receives light bouncing off the Earth's surface, and it records how much light bounces off at different frequencies. So what you need to know to compute this vegetation index, it uses, like, how much green light, how much near infrared light, and plants reflect a lot of both of those, and plants reflect very little red light, so so you kind of have the ratio of one or the other. But that calculation wasn't done by us, so you can just download NDVI from NOAA, I think, the National Oceanic and Aeronautic Administration. There's a few kind of portals where you can download this stuff in like a 5-day period, and then you just get kind of the area you want with this extremely large image, basically, with lots of pixels, and each pixel might be like 100 meters square or something, a vegetation index. Yeah.
What did you ask me to get a hold of MTN data?
What did we have to get? This wasn't MTN, actually, but yeah, telecoms data discussions are very lengthy things. I mean, it took us, you know, well over a year, 1 or 2 years, coming in as the UN and discussing this data partnership and how it would work. They're really difficult things to get right. So, you know, you have to get right the privacy, the legal side of things, the practical side of how data is de-identified and what protection measures are there to make sure that no personal information can get out of the analysis. So these are all things which, you know, take a really long time and are really complicated. I know that there does seem to be a move in the telecoms companies to make this data more available. So I think the good news is that in future this is probably going to get easier. Right now that's a cold comfort because it's still pretty difficult, basically, for us. There are a few data sets which have been made publicly available. So there were the data for development challenges. So there's public data for Senegal and for Ivory Coast. Outside Africa, there's also data for Italy. And these are useful data sets for playing around and trying to understand what's possible with this data, because there are many kind of claims of what can be done with this data. Not all of them probably really stand up to scrutiny. So kind of a long way of saying it's pretty difficult, and it was like a major challenge for our lab for a long time to get access to this data. Okay, well, if everyone's curiosity has been satisfied about the examples, then let's go into the kind of tools here. So if it's spatial data analysis, then a lot of this work is going to begin and end with some kind of GIS tool. You know, a lot of the data comes in the form of shapefiles of various sorts, or geotagged, georeferenced images, or something like that. And there are some excellent tools around to be able to put all this kind of data together and get it in a format where we can do some more kind of processing on it. Often the GIS tool, I mean, they have fairly advanced processing just within the GIS tool. It might be that you just download QGIS, get the shapefiles of the different stuff you want to see, and actually somewhere within the menus of all of this, and amongst all the plugins that you can download for these, it might just do what you want. Many of the things I've shown you could in fact just be done directly with QGIS. For those of you not familiar, we won't go into a lot of depth here. The idea is not to really give like a GIS tutorial as such, but you know, some more data science-y specific stuff. But nevertheless, to give a feel for people who aren't aware, and just to kind of set the stage, we might think of a few different basic types of geospatial data that we may have to process with. And the function of this kind of GIS tool is to take lots of them and to be able to process things in relation to each other or to themselves. The first type of thing that you might think of is polygon data. So you have something like, these are the sub-counties of Uganda, and each polygon has like a shape. It might have a shape with many parts, and it's got some attributes. So for each of these little shapes here, we have a kind of row of different values of different types. So for each sub-county, we might have its population, the average income of its inhabitants, the number of schools there, and that kind of stuff. Okay, so that's polygons. Line data is also something which is a thing. Here we can see the road network in Uganda, and so this is basically made up of a bunch of polylines. So one line might have multiple points along its path, and so this is quite different, right, to polygons. The types of things that you can compute with this are other types of questions we can answer, and we'll look at one specifically later on in the practical. The other type of data is raster data. Now this is actually like a kind of image, and what we're seeing here, it's an image, quite a large image, some sort of tens of thousands of pixels wide and high, each one representing 100 meters square within Uganda. And so it's in the form of a geotiff, which is quite easy to drag and drop into this kind of GIS program. And each of the channels, this has, I think there's a few channels in this one here, which is showing population within Uganda, estimated for each of these 100-meter grid cells. And it's like a special image which also has some geographic projection. So for each pixel, which is supposed to be 100 meters square, you know exactly where is that 100 meter square. So one of the main functions of this kind of tool, like QGIS, is to take these things together. You know, maybe we want to say, like, what's the population within a particular sub-county? You know, we take like this sub-county here, and we want to add up like how many people are there, or something like that. Or we want to know, like, tell me about like the roads within that sub-county, something like that. And then as you might look sort of closer and closer at that, and do this on different scales. Okay, so we won't really go into the details of here, but there's a bunch of stuff for kind of like doing all the kind of things that you imagine could be obvious, like take this polygon and add up the stuff inside it, or join all these polygons together and like merge the statistics in some way, or compute some other things, like what's the area of this polygon or the perimeter around it, and all of these can be output in a form which is then easy to read into something like Python. Okay, so we'll move to the Python stage. Any questions about this sort of GIS? I think I'm going to put away the GIS tool and we'll only be looking at Python for the rest of the talk. So any questions about QGIS or like how to get this data in and out of the system? Could ask that now. Yeah. Okay. QGIS is open source. Yeah. Alrighty. So, oh yeah, sorry, yeah. So the question is, if we get data on like districts, then how do we do stuff with that? Yeah. Well, one of the I guess a core function here is to be able to read in lots of different types of geospatial data. So imagine this comes with in the form of like a a CSV file or something. Then those are quite easy to add in. You just say like add a delimited text file, which could include like a something like a CSV file or something with values. You can do things like spatial joins. So if you have a list of the districts with the name and like the polygon of each one, and you have another text file or a spreadsheet or something with like the name and like the values that you've got from the district level, then you can join them together so that you get one shapefile layer which has both the name and the polygon, the actual geographical details, and the value that you want to see. So that's another kind of thing, which is also quite easy to do in Python. Actually, we might try and look at that if there's time in the practical. Yep. Yeah, great question. So does it automatically register if there's like different questions? Different image registration. Different ways to answer this question. One is the different image files have their like projection information within each. So they'll say like where is the top left and bottom right pixel and what kind of coordinate space are we in, and then you can overlay them. So as an example of that here, let's have this. Here's another image which we can think about. And this is the elevation. So this is another thing which comes in image format, and each pixel is like the height, the average height of the land at that position. And so you can. We have to make this a bit transparent so that we can see both. You can't see both very well because the population is just there's just lots of people basically. But yeah, so it will handle the two images with their different coordinate systems, and the pixels don't quite sort of match up, but you can do stuff like produce a third image as a combination of these, which is on either of the coordinate systems of the two images or on some new coordinate system that you specify on some new grid, and it will just kind of try to do the right thing basically. Yeah. Okay, so let's imagine you've got various kind of spatial data sources of some kind. Maybe they're immediately ready to use, like they're in some kind of file that you could just read directly with Python. Maybe you've had to load them into a GIS and like clip to the area that you're interested in, or compute some combination of things, like what's the population in areas higher than like 2,000 meters altitude, or whatever crazy thing you're interested in, or where there's like the number of the road density is greater or less than some number. Whatever it is, this stuff's really good for that kind of thing. And then imagine now you have that data and you want to do something a bit more than just kind of basic summary statistics, basic combining of stuff. So let's look at an example of like spatial prediction, which is one of the key topics in spatial analysis, where you have observations at some places, and you want to guess what's going on at some other place that you've not observed. And so that's a really common problem. It's not obvious to do. It's not something that the GIS packages particularly specialize in, and that's where something like Python and its geospatial tools really kind of become pretty useful. So let's look at an example. I was trying to find spatial data sets with interesting kind of patterns to do spatial prediction, and the data set here was inspired by a conversation I overheard in a shop in the UK a few months ago, and I heard someone saying to someone else, of all the people I've met called John, I've never really liked them. So I was like, well, that's funny because I've liked everyone I've met called John. Fast forward a bit later, and we're looking at a really interesting data set of names, which comes from the electoral register. And the electoral register has about 15 million names with like district, sub-county, constituency, and geographical prevalence of different names. And this is fascinating. Lots of names tell a very specific geographic story. It's surprising how it can go down to. Maybe we'll look at that later. For kind of other people's names, if they want to see like where in Uganda their name kind of crops up. This is a really interesting data set. So what I've done is taken a subset of that data set, and we can't really answer like how likable the Johns are, but at least we can see where are they and try to predict for regions that that I haven't included in the subset, like what are the density of Johns across Uganda. So first thing we've got to do is read in our data here, and so I've just prepared something in a simple CSV file where there's different kind of constituencies with longitude and latitude, and with each I've calculated this measure of like how many Johns are there per 1,000 people, J per K as it's known as the technical terminology. I'm not sure I got the scaling right here. This may actually be Johns per 100 or per 10,000 or something. I'm not quite sure. It doesn't really matter. The spatial distribution is still there. So we can read this in, and as usual with any data set, the first thing we do is probably want to look at it. Reading tables of numbers isn't really what our brains are optimized for. So let's get the visual cortex going on. So here are the points which I've kind of selected for this example. The whole point of this kind of spatial data analysis is where you have incomplete data, right? Like there's something you're trying to predict that you haven't just measured. So that's why I've left out like most of the data from the voters register to see if what we can do with an incomplete set here. This is pretty interesting. Like we have this sort of concentration of Johns around here. There's a kind of John dead zone up around sort of Gulu, like mid-southwest, reasonable, and then there's areas up here where we don't have a lot of information. It's quite sparse. This is the Karamoja, so it's an emptier place with less data. So that's one visualization. Just kind of one thing about visualizing this kind of stuff is this is something which I personally find helpful. Maybe it's a matter of taste and doesn't come out all that well on a projector, but this kind of color scale here, this is, what are we using here? This is the plasma color scale. There's a few of these color scales which are perceptually uniform, and they help to get a feel for data. So perceptually uniform, if you look at how dark this is and how light that is, it's kind of a uniform scale. And many color scales aren't really like that. They have sort of discontinuities, well, not discontinuities, but they're kind of nonlinear. So that's kind of tip one, is using these perceptually linear things. So there's Plasma, Viridis, a few others. You can find them in the matplotlib documentation. And then the other thing is often they're kind of dark to light, and if you look at it on a dark background, then the clusters kind of jump out at you. So just personally, that's something I find helpful. Now, visualizing the data is good with any data set, to try to look at it from different angles and in different ways and, see what we can see that seems to make sense. When it's spatial data, then you kind of have some extra stuff to try to put it into context. We're not just looking at any old, our inputs are kind of long and lat, aren't just any old numbers, they're positions in physical space on the map. So to help make sense of this data, we probably want some contextual stuff. And so I've got a function here that you'll find in the practical, which kind of adds a few contextual details. So there's like water bodies and roads and like major towns and that kind of thing. So rather than trying to figure things out based on the sort of outline, we can see that. So a good kind of cluster, like for my predicting generally how many Johns there are, looks like kind of northwest of Mbale is, that's kind of looking good. And there's a few kind of interesting features. So loads of names are like this, by the way. I think maybe we'll try and play around with that later on. You can suggest me your names you want to see, especially if they're Ugandan names. That helps because there's more data. But often they do have these kind of really interesting smooth patterns. I hypothesize that it's like a name becomes fashionable in a certain place. Like probably when you're naming your child, you're maybe influenced by like your neighbors or something like that, or your community, or I don't know. So maybe there is this that explains this kind of spatial smoothness thing. Maybe it changes over time. I'm sure there's people who really know all about this, like nominogeographers or something. Who there's probably whole textbooks about this. But anyway, it's kind of interesting to look at. Okay, so imagine we're doing this like spatial prediction problem, and we want to know. Given some of these observations, can we predict the other ones? Like, can we build a spatial predictive model to take some of these points and be able to predict the other ones? So what we can do is split this data up. So we'll take all of these data points, and there's like a couple of hundred of these. It's not a big data set, just to have something easy to process with and to share the file. But we could equally well do this data set on many millions of points. So we've got a few hundred here. We're going to split them up into a training and testing split. So I'm going to use 80% of these for training our model and 20% for testing. Yeah, so we've got 80% to use however we like to set parameters and choose our algorithms and all that kind of stuff. And then the remaining 20%, we're going to look at the predictions of our model on that 20%. And we're going to see how good are those predictions, and that's going to be our measure of different models and how well they do, how good those models are. Okay, so I've got another bunch of code that you don't need to worry about here, which is about looking at the outputs of what these different models are, and this is to do with like making a grid of predictions. So we don't just have to predict on our test set. The nice thing about predicting on the test set is that we know what the answers are, so we can see if they're right or wrong. But we may also want to just visualize what does the model predict everywhere, just to see, what's this kind of response function, this response surface. What does that look like? So there's a bunch of code here which makes that a bit easier. Okay, so let's think now. Let's sort of get some ideas from people. Like, what kind of principles or what ideas do you think might be helpful for taking some of these observations and trying to predict the value in the places that you've not yet observed? Over to you. What do you think? And let's start with the kind of simplest things first. In fact, what's the simplest thing you can possibly think of that might like have some kind of prediction? Is there some principle that you could explain in like one short sentence that like might be some kind of way of predicting stuff? Yes, please.
Probably do some simple regression.
Yeah, sure. Great answer. Yeah, it could be like any kind of regression method could be useful for this. Like just because it's a spatial data set, like the we've got these longitudes and latitudes that we know have this particular interpretation of like places on the Earth's surface. But it's just, we're trying to predict this thing here, our kind of target variable, j per k. We've got some inputs, which here are like longitude and latitude, and so we're trying to guess this number from this number. So really, it's just a regression problem, and any regression method should work, should be in principle applicable. Okay, so what kind of regression methods are there, particularly simple ones? What kind of like simple things could we do that maybe we could go back to the dots here. So it's a regression method, but what kind of stuff could that involve particularly? Yeah, could use a Gaussian process. Yeah, sure. Yeah, we could try that. That's sort of more that's a good idea, and we'll show the results of that later. That's like a pretty high-tech thing, you know, pretty much at the complex end. So good answer. We'll save that a bit till later. In terms of starting off with the simplest possible things, like what's the simplest thing you could do? Imagine you've got these data points here. Someone asks you like, what's the value there? What's a super simple thing you could do? Super quick and super easy.
Maybe you look at neighbors.
Maybe you look at neighbors, right? Yeah, that seems like a simple thing. Yeah. You could look at many neighbors. You could look at one neighbor. That's completely true. Yeah. There might be some stuff even simpler than that. Sorry? Inverse distance. Okay. Yeah. So you could take the neighbors and you could like weight the neighbors by their distance or something like that. Yeah. Or weight them by some kind of inverse distance. So the nearer of this point here, like maybe you weight these ones which are close by heavily and these ones which are further away, you weight them less or something, have some weighted sum. Yeah.
Just the average?
Just the average, right? Yeah, sure. I mean, that's about the simplest thing I can think of. Yeah, like let's just take the global average of how many Johns there are per 1,000 people, and we'll just say wherever you predict on the map, like that's the number. Yeah. Okay. So let's think about that then. Of the suggestions we've had, let's kind of order them in terms of complexity. There's like just the average. Just predict wherever you are. Just say it's the mean of like whatever the values that we've seen are. So no spatial pattern at all. That's like a real simple thing you could do. Then you could take neighbors, and neighbors you could take like the one nearest neighbor, right? That would be like real simple, but a bit less simple than just predicting the overall average for the training data. You could say if this is our point here we want to predict for, then which is our nearest neighbor? Maybe it's like this one here, and we could say, well, that's our predicted value. Okay, that would be like a little bit more complex of a model, and maybe then we start getting in some spatial variation. Then we could take like more than one neighbor. We could say like, give me the 10 nearest or something, and like, what's the average value of those? Then next thing we could bring in is like weighting by distance. And then after that, we could go all the way to Gaussian processes, which is actually kind of a similar concept to distance-weighted nearest neighbors, but with some extra kind of fancy stuff that we'll talk about. Okay, so those are a couple of ideas. I think those are all good suggestions. And anyone else have anything to add before we kind of look at how some of those do? Regression methods could be. There might be lots of them. Okay, well that'll do us for now. Actually, we're getting a bit low in time in this session, so let's fire on. Okay, so this idea, the super simple thing of like the average, like this is about the simplest thing you could do, but it might not be far off in a lot of cases. You know, if particularly where there's not a lot of sort of clear spatial pattern or something, it might make sense to just take an average of what's going on. Like in average in Uganda, how many Johns are there per 1,000 people, and just predict that everywhere. You know, it's probably not going to be miles off. There's probably not places where there's radically more or less Johns than everywhere else. So, you know, it might not be a bad thing to start off with, and particularly to compare the performance of the other methods. Okay, so what we're doing here is we're getting this like y-pred, and we get it by setting up an array of ones of the size of the test data set, and we're going to multiply that by the mean value of the training data set. So whatever value the mean of the training set is, we're just kind of predicting that for all of our test points. And then we're computing this thing here, mean absolute error, for the test set and the predicted set. So mean absolute error just means, like, for every prediction you make, you see how far off it was, positive or negative. You make it positive. That's your distance, how far away you were. You know, if the right answer was 3.5 and you guessed 2.5, then the absolute error for that is 1, and you average that over all of your predictions. So in many cases, it's not actually the ideal error metric, but here it's kind of useful because it's on the same scale as the data itself, and it kind of gives us a rough idea of how well things are doing in a conceptually simple way. Mean absolute error can have some issues. Can anyone think of where calculating mean absolute error, you know, you might get like a low score or a high score, but that might actually be misleading? Is there any way you could get like a high score for mean absolute error, but actually your model's doing quite well, for example? What could go wrong with mean absolute error? Yeah.
Let's say you overfit a model. Then you find the mean absolute error. Definitely it will be small because of the model. So that's, to me, that's one of the situations where you might have a small mean absolute error, given that you really overfitted the model.
Yeah, right. Indeed, yeah, yeah. That's a big problem actually in practice, that you can. So you can also do this. You can overfit yourself as well, even if you're really careful about training and testing sets. As you try lots of experiments on the same training set, you might get closer and closer to low error, but it's just that you're overfitting for those particular data points. Another thing about taking absolutes is, imagine you got the right answer for all but one of the data points exactly right, and then another one you got really wrong. Then the absolute error might look, you know, might be misleading. There's a few things like that. Okay. Anyway, nevertheless, we've got like this score. We've got this kind of, on average, how wrong do we get it for different points, and we're getting it wrong like 0.381, which isn't too bad. I mean, predicting the mean, you know, sounds simple, but it's not a bad start. You know, if we look at the kind of scale of these things, they're on a range of like close to 0 to sort of approaching 3. So if we're on average getting our predictions wrong by like 0.3, that's not a disaster. But let's see what happens when we try some of these other ideas. Okay, so in particular, let's try this really simple idea of just saying, well, let's make our prediction be whatever the closest data point was. Let's take, you know, you want to know here, we didn't observe anything there, but we did get some statistics on like here, which is really close. So let's say whatever the average there is, then that's what our predicted value is going to be. And I'm going to do not just the prediction and calculate the mean absolute error, but also show what the predictions would have been across the map, because that gives us some really useful insight into what our model is modeling and what kind of things it predicts around the place. So here's that prediction. Maybe I'll turn off the other stuff a moment so you can kind of see what's going on. Okay, so here's what the model predicts across the whole of the space, and we can see our mean absolute error has gone down quite a way. We've gone from 0.381 to 0.169, so we've like halved our error here. Pretty good result for like a simple thing. And the spatial patterns are starting to emerge here, right? And we get these funny sort of shapes which are defined by the area which is the closest to one of the points. So it's this kind of Voronoi tessellation where you know, we see like, you know, areas which are the closest to a single point. And we're starting to see like northwest of Mbale. Here's our hotspot. Here's the John's dead zone. You know, we're starting to see some of the familiar things from the, you know, around Arua's, like doing reasonably well. So we're starting to see some stuff here. Okay, so not bad. Maybe we can you know, we can make this model a little more complex, and we still might not be getting to overfitting stage, right? So let's see what happens if we add on a couple of neighbors. So as we add them on, we get this like smoothing effect. We're now combining at a single point like lots of these neighbors together. Interesting, our error went down, right? Up. It was like about 0.16, 0.17, and it's gone up to like 0.19. So interesting. Maybe that was the wrong number of neighbors. And actually, if you keep going, then you know, it seems to kind of get worse. So that's something to look at. Like, how do we kind of fit that stuff? Remember not to fit on your test data. If we do this too many times, we'll start overfitting ourselves, and so we need to be a bit careful about that. Next example was using the inverse distance. So all of the great thing about doing data science stuff now is that everyone's written all the algorithms to do almost everything you ever need. So you know, you don't have to go into all the details and have a week of excruciating you know, debugging where your colons were supposed to be and where you're, you know, indexed by 1 and it was supposed to be by 0 and all of that. Like you just write weights equals distance and it just does what you just had. So let's have a look at that. That seemed pretty interesting, right? So we're getting these sort of hotspots near where we've got measurements and pretty interesting looking map emerging. I think we're starting to get into some pretty serious models, you know, which might actually be, if we really had a formal request of like predict us the density of Johns across Uganda, this is the kind of model that we might consider like releasing for practical use. So you know, from this data here, we've gone to like this type of like model response across the whole place, which looks kind of credible. Yeah, I don't know. Maybe I'm biased as the creator here, but and so you know, that seemed to help, right? Like if you look at the mean absolute error was 0.9. I think 10 works a bit better, didn't it? Okay, so 0.176. As weights uniform. 0.1999, so that seems to be better. Okay, so that's one kind of thing. And last thing, we also had a suggestion of Gaussian processes, which does make a lot of sense and is often a standard methodology for geospatial stuff, where they call it kriging. And the Gaussian process is a type of model which basically says, it's something similar to nearest neighbors. It says that like if points are close together, then they're more strongly related. And the further away they are, the weaker that connection becomes. And so you get this interesting and useful effect from Gaussian processes, where when you do a prediction, it gives you not just the response, the number, but also a measure of how uncertain you are. Because if you try to guess the value at a place far away from where you've observed, then that value is less certain, right? And it's useful to have some idea of like not just what the predicted value is, but how confident are we in that prediction. We call that the variance of the prediction. So the key to all of this kind of things to do with Gaussian processes is defining exactly what do we mean when we say stuff is close together. And that turns out to be, you can use a sort of simple default, but there's a whole world of stuff to get into there. The kind of default that we'd often use is this kind of squared exponential, where we take an exp and we have like the where the 2 points are, and we have some kind of length scale. So we want to have some concept of like how close is close, right? And this is going to be quite different for different problems. So we've got to set this length scale somehow, and we can think about how to do that. Let's start with a guess. Let's say whether you name your child John is probably related to like whether the people up to about 30 kilometers around you are naming their child John. Now that may or may not be a good guess or not, but at least it gives us a start, right? We can set something length scale 0.3 degrees in this unit. Luckily for us in Uganda, like we're on the equator, and so like degrees are a really natural coordinate system. It's not so good in the UK. You have to convert to all sorts of other coordinate systems. So maybe that's why it's a bit easier for us there. Okay, so this is the kind of output we get. Density of Johns per 1,000 people across the map of Uganda with a Gaussian process with a length scale of 0.3. Maybe we think that 0.3 is a bit close. Maybe you're like 30 kilometers approximately is kind of a bit close. Maybe it's more like 100 kilometers, and actually it should be much smoother than that. It's kind of there's like longer range connections. And then you get this kind of smoother map here, right? That would like correspond to making that assumption. Or maybe we think 30 kilometers is much too much, and it's only like 10 kilometers. And that wherever we've seen those many Johns, it's just in that place, and everywhere else we haven't seen it goes to some mean, which here is 0, but actually should probably just be the mean of like how many Johns per 1,000 other in general. Or what we can do is try to automatically optimize this, and just figure out, like, by taking the training data and doing various clever stuff that's probably difficult to describe in like 0 minutes. Just find the value which fits the best, and that looks like it's sort of about 50 kilometers or so is the right kind of length scale for this problem. And there's the mean absolute error that comes out of that. So this mean absolute error is, you'll notice that some of them, just using kind of distance weighted nearest neighbor, actually got a lower error score than that. But the point is that when you have the ability to specify a model with different types of knowledge about the problem, then that's an opportunity to make this model a better fit. So we've just kind of used this thing here, this kernel, which is a way of saying like how close is close. And we've just used this default thing of like it's the same in all directions, and we don't care whether it crosses water or anything like that. But these are all things that we could build in, right? We could build in that knowledge into our model. We could define it as like some kind of kernel or distance measure, and then that might give us better prediction still. I'm going to wrap up, and we'll sort of get more into this kind of stuff into the practical. But just one thing here is the way that we calculate distance, for example, with a kernel, doesn't just have to be like how many kilometers is it in a straight line from point A to point B. And maybe one interesting thing is stuff like the road network, which we saw earlier on, one of the examples. Maybe the best distance from like here to here isn't just sort of how many decimal degrees is it like from the point. It's like what's the shortest path on the road network, which in fact there's a big water body there, so that might help sort of define. And then all of these things, like where we're saying kernels and Gaussian processes, or like what's nearest and nearest neighbor, we have this distance weighted thing, inverse distances. That doesn't have to be just a straight line on a map. It could be like the shortest path on a road network. And there's a whole load of other excellent tools to help compute that kind of thing, like from here to here, tell me, given the average speeds of all of these roads and all that kind of thing, like which is the best route to get from there to there, and how long does it take? And if those are the kind of distances you use in, then you're really getting into some pretty interesting predictive spatial models. Okay, so I'm going to stop there. Maybe we've got a minute or two for a few questions. I know we're splitting up later into 2 practical sessions. IoT is going to continue, and then for those who want to do spatial analysis, we'll do a little bit here. And what we're going to look at is kind of optimizing these parameters. So if you decide on some model and you want to choose the parameters, how do you do that? And then we'll see, who can get the best kind of test predictions for this problem. Okay, so time for a few questions, if anyone has any. Yes, please.
Maybe in that example, one interesting thing to look at is like the age. If you have the age in the data set, maybe a name like Obama would think maybe they're around 10, 12 years old. So try to guess what happened, change to the name.
Yeah, true. We don't have any information on how old these people are. Yeah, so maybe this actually is like a spatiotemporal prediction problem. We're dealing with it spatially, but you know, in 10 years' time, the map might change, right? Maybe John's kind of getting old-fashioned and it's like dying out, you know, and Obamas are everywhere, and you know, indeed. So we don't have any sort of notion of time in this data set, so unfortunately we can't use that component. But that's a good point. If you really wanted to predict, if you wanted to do this problem for real, then that would be a good thing to include. Yeah.
Okay. Interpolation is fine, but extrapolation. Let's say now you want to find out about the densities of John in the nearest country, maybe Kenya. Based on existing layers that you have in Uganda. Let's say about maybe Johns are likely to live closer to roads, near towns.
Right.
Incomes are a bit higher.
Exactly that, yeah.
Okay, so we have those layers in Kenya. How can we extrapolate that information? Instead of just spending more money doing another survey in Kenya, how can we use this information to predict what's...
That's a superb question, brilliant. So the question is, yeah, for those who didn't hear, how do we go outside? You know, maybe we want to make predictions for somewhere completely different, and we want to make predictions like over here. Then just saying like what's close to a place we've observed probably isn't going to help, right? Like it's just going to give us this average. And we won't really get any spatial variation. So, you know, thinking back to the concept that all of this spatial prediction is just a regression, and we're just taking two input variables here, longitude and latitude, and we're trying to predict this output variable, the j per k. And these longitude and latitude could have been anything, right? We could have done, when we were looking at our GIS earlier on, and I was saying about, you know, it's a useful way of taking layers and kind of computing different things about them and getting in them in some format. You know, we could use that kind of tool to take the sample locations that we have, take all sorts of other stuff, you know, what's the altitude and like how many roads, how far is it from a main road, and yeah, what's the household income, what's the population density, you know, all these things we could think of. And those could become columns in this data set as well. And then we could do a regression. We could use the same kind of models, in fact. And instead of using the spatial information, if we think we're going to do a prediction, if we're going to need to do a prediction where the spatial information might not be that useful, then maybe we need to predict from that other stuff. But it's basically the same types of models that we could use. Yeah. I think we're getting to time where we need to make a stop. So for those of you who are interested, then I think in an hour's time we'll do a bit of practical work on this. Okay, so that's it for me. Thanks for your patience. We'll see you later.